Hi guys, today I'm going to discuss a question based on GCD. So basically the question is pretty simple. Basically you would be given two integers a and m and you need to find all the x belonging between 0 to m such that on adding it with a and taking GCD with m we get the same GCD of that we get by a and m. And pretty much like, let me explain you this by two different methods. Firstly I would be explaining this by Euler Totient method and the other one by bit uh, bit set rather. So what we are given is that GCD of a plus x should comma m should be equal to GCD of a comma m. Let it be k, and where x belongs to 0 till m minus 1. Basically, by this I can also say that GCD of a plus x comma m is equal to GCD of a plus x modulo m comma m. Okay, so now this a plus x modulo m for any number after taking its modulo with any integer, we get all the numbers from 0 to that mod minus 1. So basically here I would be getting all the numbers to 0 from 0 to m minus 1. Basically now using this condition I need to find all the numbers that satisfy this all the x such that after adding it to a and taking it mod with m we get some integer between this range. So now let me move forward. A plus x comma m is equal to g. Now suppose this let me take it as p only. So now we and where the GCD of g and this p has to be equal to 1, as if there is any other common factor then it would be definitely be considered into g. So basically now what I can say is that GCD of a plus x by g comma m by g, rather it is comma m by g should be equal to 1. Now, why this I can say? Because the maximum GCD of this and this was G only. So now after I divide this by both of them, there would be no common factor which would be present in them. Like suppose I'm taking this 8 as 2 into 2 into 2 and I'm taking this 10 as 2 into 5. Now the maximum GCD, rather GCD only, there is no word such as maximum GCD. I'm just saying that to just actually interpret that I'm taking all the factors common. So after I divide this by 2 and this by 2, you can see that the factors left here would be only 5 and here it would be left as 2 raised to the power 2. So basically now there is no any other common factor which can be divided. So so basically now this condition has to be equal to 1. That is GCD of a plus x modulo m by g comma m by g has to be equal to 1. And now by that the definition of Euler Totient function, you know that for any integer n, phi of n represents all integers between 1 to n that are co-prime with m. Now basically here I need to find all till 0 till that number. But as the GCD of 0 comma some n is equal to n and GCD of n comma n is also equal to n. So basically this logic would also work from 0 till n minus 1 also. The same logic would also work for that. Now, so let me show you that in the code also, so it would be pretty easier to understand. So here I'm just taking the test cases and after this I'm calling this function, and here this is just the same thing that I'm calculating, that is m by g. So now I would be calculating all the numbers which are co-prime to this number. So basically this is the answer variable, a is equal to x, and after this I'm just taking all the prime factors and I would just calculate all the things, and then if after that if the number is greater than 1, then definitely this has to be a prime number, and then after that I would just output that number. So now let me show you the bit based approach. For that, the initial condition was that GCD of a plus x comma m has to be equal to the GCD of a comma m. So now for this I'm taking this as a is equal to k into p, where p is some factor and k is the GCD. And M is equal to K into Q, where this is the GCD and this is some factor. And now for this to be true, I need to have A plus X is equal to some K into R, a factor. Now this X has to be, now taking this X in the left side and all things on the right side. This, I think, if this A, I can write this as this. And now by the condition given, I have this. Putting this in here, I get this as R minus P less than M. And so basically 0 less than equal to R minus P less than M by K, and adding P to both sides, less than M by K plus P. Basically this M by K is nothing but Q only. So basically our final condition comes out to be R belongs to P plus Q. Now basically here it's just that I need to find all the numbers from P to P plus Q minus 1, and for every R I would get some X, and that X has to be valid. Now for that X to be valid, I need to have this R independent of all the factors of the Q. That is what I'm trying to explain, is that suppose M was something sort of this 2 raised to the power 3 into 3, or 5 raised to the power 2, 7 raised to the power 3, some sort of this number. So basically the distinct prime factors here are 2, 3, 5 and 7 only. Okay, so now suppose the GCD of A and M was 2 only. So if this R contains any of the factors other than the GCD, suppose it contains 7 also. So now this Q also contains this 7, and this factor A plus X is equal to K times something, and this also contains 7. Then this would imply that the GCD of them would be multiplied by 7 also. So the GCD of A plus X, the comma M, would now not be equal to GCD of A comma M. So for avoiding this, I just need to do this one thing. I would firstly divide M by G, that is M is this, and rather G is M by K. So basically now I would get a number. Suppose it's like this 2 into 11 into 7 into 3 raised to the power 2, 3, 1. The powers here actually don't matter. So now from all the numbers between P to P plus Q, if I remove all the numbers that are multiples of 2, 3, 7, 11, then I would get only those numbers which aren't divisible by any of this, and hence the GCD of those numbers with this M by G would be equal to 1. That is, this this M by G and this R wouldn't have anything common in them. So for implementing this, I would be using simple like class 11, 12 based approach. Now now you must be remembering the questions in class 11 was somewhat like this, that from numbers 1 to 100, find all the numbers which are divisible by 2 and 3, which are divisible by 2 or divisible by 3. So basically what you did was you divided 100 by 2, you divided 100 by 3, and then added both of them, and then removed all the numbers which are divisible by both, because for 6, 12 you counted them in this also and this also. So for that you just did this, and rather in programming you take this as floor. So I would be doing this only. So for implementing this, what I'm proving sort of this is, as the constraints were from till 10 raised to the power 9. So basically to get numbers from till 1e9, I just need to multiply and check how many numbers are maximum possible. So for checking this, I multiply the lowest primes. So 2, 3, 5, 7, basically till 29 numbers only it exceeds 1e9 limit. So basically now I would get that as only 10 factors. So only 10 primes are there such that they could be part of this, and I need to exclude all of them. So for making this, what I would do is that I would I would add all the numbers which are divisible single-handedly by those numbers, then subtract those numbers which are by taking two at a time and multiplying them, then adding taking three at a time and multiplying them, then subtracting taking four at a time and multiplying them, and similarly I would do this. Now I need to do this for every possible combination. So basically I would make a bit type of thing, bit set type of thing. So there are 10 numbers. I would be using 10 bits to store the position of the bit which is set, or rather I would insert all the primes in a vector, and corresponding to each set bit I would choose that prime number and multiply it, and then after that I would be just doing this plus minus thing. So I'm not able to convey that thing very clearly by the language. Let me show you that by code. It would be pretty easier to understand by that. So I'm here, it's just I taking the input, and yeah, and this is just I'm calculating that m by g factor which is stored in x, and now here this primes is generating prime that are is generating primes that are the factors of this m by g. So this gen pair function is nothing new, it's a very trivial sort of thing. So now this is the same thing, that is what I was showing you here, p plus q and p. So basically, I would be searching all the numbers till p plus q minus 1, and subtracting all the numbers which were till p minus 1, and hence I would get my answer. So that here it's that thing only, x plus that minus 1, and this is actually p minus 1. So now here is the bit set type of thing. So this is just the number of primes which are there. So firstly, I make a bit set of 10 unit. Then for this is actually a bit set function that is used to store any number in the binary format. So for every I from 0 till 1 or 2 raised to the power size of primes. So I would be iterating over all the numbers, and I would be calculating its bitwise representation. And then for each bit which is set, this s dot test j would return me true if the bit is set, otherwise it would return false. So for every bit that is set, I would correspondingly multiply that prime which is stored in my primes array. And now after this, if the number of set bits in that bit representation, which I'm getting by this k, which is s dot count, it represents the number of set bits in the bitwise representation. If that number is odd, then I would add that number that I showed you initially. Suppose that it was 100. It was 100, so I did 100 by 2 plus 100 by 3 minus 100 by 2 into 3. Basically, for all the odd number of multiplications, I would be adding, and for all the even number of multiplications, I would be subtracting. So if the number is odd, then I am just adding, and if it's even, then I'm just subtracting. And this is just to ensure that the product is not equal to 1, because for 1 it's just meaningless. And then I would be just returning the x minus answer, because I need to return the number of numbers which are not divisible by any of them. So I would be just returning x minus answer, and then I would be doing this for this also and for this also. Then finally I would be printing the answer. So hope you liked it, and hope you liked this approach, because this could be used in many different ways and in many different questions. So okay, I would see you later. Thank you.